Hello everyone. We are going to talk this week about outliers. And we'll talk about outliers, we'll talk about why they're bad, and then we'll talk about why they're good. So first of all, what is an outlier? An outlier in a data set is something that is basically weird. It's typically a small number of data points, could be one, could be a few, whose value is far from all of the other data points. And it could be either on the high end or it can be on the low end. Like I said, it can be a single data point or a group of data points, but it's probably not a big group of data points because if it's a big group of data points, it will have too much power in the data set and it won't be considered an outlier. It will actually throw the mean off and it will be just a widely distributed data set. So an outlier is typically sort of something that stands on its own, or it's a couple of data points that stand on their own. In real world terms, these are just data points that signal unusual behavior. And so it could be if you're looking at the average age of or the average life expectancy of a series of countries, and you happen to find a country where maybe conditions aren't quite as good as the other countries, so its average age or average life expectancy is far, far lower. So that one might be an outlier. And outliers can really make a mess of things. They can pull your averages down. They can throw your other statistical analyses off because you have to account for those outliers. So what we're going to do is take a look at a couple of examples. First thing is the housing market. I don't know how many of you live in King County or around King County, and maybe you're in Kittitas County or some other county in the state or another state. And what you hear is you hear a news story that talks about the median house prices. So we over here in King County are hearing a whole lot about the median house price in King County. There's a reason why they don't say mean. Mean house prices are far different from median house prices. And the reason why is because you have outliers on the high end. You have a number or a series or a group of houses that are in the millions, like Bill Gates's house or somebody else who's rich, their house. And so what that's going to do is that's going to take those small group of houses that are in the millions are going to take the mean and they're going to pull it way out. They're going to pull it way off. And it's going to pull it to a level where a lot of us, it doesn't really impact a lot of us because it's so far off the mark. So we use median instead to get around that problem. That is a classic example of outliers. It's just where you've got a few data points and it makes the mean an sort of invalid measure of central tendency, what we call central tendency, just because it pulls that mean so far off. And so we fall back and we use median. Another example would be national exam scores. You got thousands of students that are taking the SAT or the GRE either to get into college or get into grad school. And there's typically a mean score for all students. There's also a median score for all students. And it's interesting to look at the mean compared to the median score because that will tell you your impact of your outliers. So some of those students who take the exams, maybe they bomb their exams and they have very low scores, and that's pulling down the mean. So if we want to do analysis of the average score, the average GRE or SAT scores, do we want to include those really low scores since that's going to separate the mean from the median and it's going to pull things down? Or do we want to hack off kind of the lower quartile or the lower 25% so that we're really just looking at the scores that are there in the middle, and we can see sort of a distribution of how those scores are, maybe from 200 up to 650 or 700 or something like that, how those scores are distributed, considering anything below 200 or above 750, 600, 750, whatever, to be an outlier. So there are ways to get around outliers. We just have to figure out what the best method to use is. Let's look at outliers in our example that we did for this last week's weekly exercise. I had you compare two variables, Christmas and sales. And ideally, if Christmas and sales were linear in their relationship, you would see them fall across the linear line. That's the blue line that I have there. But what you're seeing there is a couple of outliers. Specifically, there's one that's way up in sales, right around 1,400, and yet it's registered only 100 on Christmas sales. Not a very good predictor in our model, and it is an outlier. And then you see a couple other outliers. Some of them are above the linear line, and some of them are below the linear line. And these are ones that they still have to be taken into account when you're generating the model. But the model itself, depending on the statistical method that you're using, may discount the outliers because there's so many other data points that fit the model more closely. But still, those outliers, make no mistake, those outliers are having an impact on the generation of your model. Let's talk a little bit about more data, And this is something we haven't really talked about. We're going to probably get into some basic sort of statistical stuff that you may have already learned in a previous class, or if you haven't learned it, this will be fairly simple. and it may be stuff that you've been over before and you just need to be reminded of it. So we're going to look at range and interquartile range. We'll look at mean and standard deviation. We'll look at box plots, and then we'll look at normally distributed data where we're talking about right and left skew. This is all in an effort to sort of give you more information about outliers. Let's take a data set. We have U.S. income data, and if we were to look at the entire population of the U.S. and look at every single person in the U.S., and we were to look at what their annual income is, we could come up with a data set that would have 320 million, 320 some odd million records. But that's not possible. That's a population. It's not possible. So what we do is we're going to take 1,000 randomly sampled records out of the population, and we are going to use this as a random sample that is representative of the U.S. population. And that's what we've done here. So this is our U.S. income data. You'll see that there are 1,000 records, and of those 1,000 records, there's going to be a range of income. Clearly, the low end is going to start at 0 since records 1, 2, and 1,000 start at 0. But what's the high end? What's the range of the data? Our goal is to obtain an idea of how spread out the income is in the United States. So we'll look at the range of the data set, and then we'll ask the question, do we need to account for outliers? So here are some summary statistics. And this is basically a way just to look at the entire data set. The first thing we have is what we call the 0 quartile, or the minimum, and that's 0. We've already determined that that's 0 because we saw the couple of records that were set to 0. Then we have quartile number 1, which is 8,600. That is the 25th quartile, the 25th percentile, I should say. Everything below that, there's 25% of the records that fall below that. Then we have the median. The median is 23,000, and that is basically the 50% mark. So 50% of the incomes that we recorded fell below 23,000. Then we have the third quartile, or the 75% percentile, and that is $48,000. And basically what that means is 75% of our records that we recorded fall below $48,000. Then you see the maximum, or what's often referred to as the fourth quartile, and it's 1.2 million. Now there's a huge difference between 48,000 and 1.2 million. And then we look at the mean, and the mean is 37,486. That tells you pretty clearly that you've got a couple of gigantic outliers that are sitting out there on that end that make up that fourth quartile. So if we want to calculate the range for this data set, what we typically do whenever we calculate the range is we take the maximum value and we subtract out the minimum value. And that gives us the range of variation from the smallest to the largest. In this particular case, it's pretty easy because our maximum is 1.203 million. Our minimum is 0. So we're basically subtracting nothing from 1.203 million, and that gives us a full range of $1.203 million across our income data set. That is a huge range, and that makes the range pretty difficult to work with, and in a way a little bit useless, because we know that most of the data set that we have is far, far, far away from that 1.203 maximum. And it could be just one person. So the range is sensitive to outliers. After all, perhaps only one person has an annual income of 1.203 in our data set. It's still part of our range, and it's still an outlier, and it's still something we need to deal with. So we need a measure of variability to get around this. We need a measure of variability that's going to help us that is insensitive to extreme values or insensitive to outliers. And what we're saying there is we're looking for a way of being able to measure that range, a useful measure of the range that won't take into account those outliers. And that's what interquartile range is. Interquartile range is a way of being able to measure the range in a data set and take out the outliers. So we can eliminate some outliers and some outlier problems by using the interquartile range, or IQR for short. What we do in this case is we take the third quartile, remember that's the point at which 75% of the data points fell below that, and we subtract out the first quartile. Okay, so I believe the third quartile was $48,000 and the first quartile was $8,600. What that does is it gives us the range from quartile 1 to quartile 3. That by default is going to shave off the outliers, and now we can work with that data set because it's going to give us a more meaningful range. It is going to cut off some useful data sets. There's a lot of data set that is lower than Q1, a lot of data in the set that's higher than Q3 that's still useful data, and we're going to sacrifice that in order to get a range that is actually more useful. So now if we look at this, we see that Q1, like I said, is 8,600, Q3 is 48,000. We subtract 8,600 from 48,000 and we come up with 39,400. So 39,400 is going to be our interquartile range for this data set. Gets rid of this, which is our maximum, probably an outlier, might be just one person. Also gets rid of my minimum, but it also gets rid of a lot of data points in between the minimum and Q1 and Q3 and the maximum that we may actually want. So we have to be careful with the use of interquartile range. All right, let's talk about mean and standard deviation. These go back to basic statistics. We know how to calculate the mean. The mean is basically add them all up, divide by the number of numbers that were in the column or in the row or in the set. We can also calculate the standard deviation, and if you ever need to calculate the standard deviation, you can identify the column for which you are calculating the standard deviation, and you can use the stdev function in Excel, and it will calculate out a standard deviation. But what does this tell us? So a standard deviation that is small means that most of the data points that are in the set are close to the mean, and it's what we call a tight scatter. It's a tight scatter around the mean. You've calculated a mean, and most of the data points are really close to that mean. A standard deviation that is larger means that many of the data points are spread away from the mean, or a loose scatter. You're still calculating a mean, but the data points that were used to calculate that mean may actually be far away. So the big ones are offsetting the smaller ones, and you come up with a similar mean. In both the two examples of a tight scatter and a loose scatter, you can have the exact same mean. It can be the exact same value, but yet you can have a tight scatter around one and a loose scatter around the other, and that is a big difference. So in the second example, it's more likely that we're going to have outliers because we have that loose scatter. So there's going to be some that may be really far away. You could potentially have outliers in what you consider a tight scatter as well, but there's probably less of a chance of that happening. So let's look at an example here. We have mean with a tight scatter. Our mean in this data set is 6.5. And you look at the scale over here, we go from 0 to 10. If the mean is 6.5, there's not a lot of variation along this mean. Everything's a little bit above or a little bit below that. We have a standard deviation of 1.81. So that standard deviation of 1.81 basically is telling us that there's not much room between the mean line and each of the data points. In my next example, we have a much larger scale over on the left-hand side. And so that is kind of masking a little bit the difference between the two examples. But what you can see is that you can see that I have a mean of 13.9 with a standard deviation of 9.7. That's a big standard deviation relative to that smaller mean. And you can see that I have one big outlier here, which is about 38. And then I have a couple other outliers out here. This one is all the way up to probably 28, 29, with a relative, quite a ways away from the mean. So this is a much looser scatter around the mean, and it has got a couple of outliers built into it. Now if I was to eliminate this outlier here, what that would do is that would tighten up my mean a little bit. It would lower my standard deviation, but I would still have some of these other ones to contend with that are pretty far away from the mean line. So do I drop the outliers? That's a question, and it's a good question, and it becomes a completely situational decision. It's important for you to understand that if you decide in a data set to drop your outliers, what you're doing to your data set is you're limiting your data set. You're taking a subset of your data or a limited part of the picture that you were trying to sort of project with your data. So I think you really need to think about how it's going to impact the rest of your data and how it will impact the results of your calculations. So there's a big decision as to whether or not to drop the outliers. Some things that might help you. We could look at a few tools, things like a Boxplot, a histogram, or normal distribution graphs. So let's start first with the Boxplot. A Boxplot is a tool that is used basically to tell you a couple things visually. First thing it tells you, there's your mean. The second thing it tells you is Q1, right there is that bottom of the Boxplot, and right there on the other side is Q3. So you see the range. This is your interquartile range between Q1 and Q3. Then you can also look and you can see whisker on the right-hand side and the whisker on the left-hand side. What the lower whisker means is that I'm taking quartile 1 and I'm subtracting out 1.5 times the interquartile range. So I'm taking this value, multiplying that value by 1.5, and I'm taking it all the way down from the other side. And I'm doing the same thing on the upper whisker. I take Q3 and I add in 1.5 times the interquartile range and I put it on the other side. It looks a little unbalanced, but that's probably because of the placement of the data. What this allows me to do, though, is if I'm looking at my data points, and my data points were all plotted on this plot, they should all fit within the whisker plot. They should all fit within this lower base and this upper base. Anything that doesn't is probably so far outside of my data set that it is a true outlier. And this data point right here would be an example of a true outlier. It would be one, if we're looking at life expectancy and we're looking at several different countries, we start here at about 62 and we go all the way up to 79. And of the maybe 50 countries that we look at, they all fit in here, except for this one country down here, which is truly an outlier because it's at 54. We may choose to drop that from our calculation because it unnecessarily messes up what we're trying to do and pulls the average off. So that's a decision that the researcher has to make. Histogram is another way of being able to show this. A histogram will show how many data points are within a given interval. So we divide our data points into bins or intervals, and we plot those out in the histogram. And here's an example of what that looks like. So we see for the same life expectancy data, we see that we've got something that falls below 60. It's about a measure of 1. That's our 54. Then we've got some 62s in here. We saw that the data set started at 62. The vast majority of our data are right around 65 to 70, 75, and then we don't quite get to 80. Even though it's marked here as 80, we stop out at 79, but it's getting close to that 80 mark. So a histogram lets us see kind of how the data sort of plot out and how the data sort of look. Then we can decide whether or not we want to drop the outliers. Do we drop the 79s? Do we drop the 54? And we just focus on these. Again, that depends on what you're trying to do with the data. And lastly is the normal distribution. You've all seen this as a bell-shaped curve. The normal distribution allows us to determine the extent to which we think the outliers are really going to mess up our data. So what we can see is right now these are both perfect normal distributions, and we can see the extent to which, there are any data points here. It wouldn't necessarily look all pretty like this. It may be a little skewed to the left, a little skewed to the right. It may not be quite as bell-shaped depending on the number of data points that are in there and the like. But again, it's a tool that allows us, once we've plotted our data set, we'd be able to see how many data points we have over here on the right tail or how many data points we have over here on the left tail. And if there's a large number of data points over there on the left side tail and it's going to sort of throw that off, then we might want to include those in the data set, include those in the analysis because there's enough of them that it matters. But if there's only one, we're not going to be able to see it that well, and so we may throw it away. Now, both of these are actually put onto a standard distribution, which basically means we've normalized the mean to 0, and then each one of these sections is one standard deviation away from the mean. Not really relevant here, but that's what accounts for the data that we've got set up, the way that we've got the scale set up here. So again, using a normal distribution, we can actually plot along a normal distribution and we can see the extent to which there is either a bubble of data that shows in one of the tails, or we can see if the mean is being thrown off. And that's kind of the concept of skewness. Getting back to the concept of mean and median. If we have a data set that is not impacted terribly by outliers, then our mean and median are going to be fairly close to the same. That is a general rule, but it's typically a pretty accurate rule. So mean and median will be probably pretty close to the same. But if we get a data set where there's a lot of outliers or there's strong outliers, then our mean and median are going to be different, and they're going to be substantially different. And then when you plot that on a normal distribution, you can see the results of those outliers because you'll see that the mean and median are in fact kind of out there, and they're very different. So let's take a look at some examples. This first one is skewed left. And what that means is that you have a large number of outliers on the lower end. And what that's done is that's pulled your mean down towards the lower end. And that is having an impact on your overall distribution of your data points. And you'll see that there's a big difference between mean and there's a big difference between mean, and that's because you have lower end data points. On the other side, on the far other side here, we've got data points that are high. So we've got outliers that are high, and they are pulling the mean over to the right side. And so there is a big difference between mean and median, and it's because of the higher end data points. In the middle, this is where we probably don't have a lot of outliers at all. And so the outliers aren't really having an impact, and mean, mode, and median are all the same. That's rarely going to happen, but it could. Or there's going to be such a small difference between them that it won't really matter. But right now you can see how there's really no impact of outliers here. So let's talk more about outliers. Okay, it seems then the best thing to do is to get rid of the outliers, right? Or limit them. And they don't just mess with means. Outliers actually have an impact on things like correlation when we're trying to sort of look at the relationship between two variables, variance when we're trying to see if two variables change in a similar direction, the linear regression that you've just been working on, the outliers impact that as well. They all suffer at the hand of outliers. And many statistical models are actually designed to eliminate them or correct for them. Or you'll see that statistical models will look at each data point and will assign each data point an error or an error bar. And if the error bar is wide, then you tend to discount that data point. The outliers oftentimes will get wide error bars, so they'll get sort of eliminated from the analysis anyway. But in using data and analytics, there's a different story here. When we're just looking at the numbers and we want to get clean numbers, then we might want to eliminate or reduce the impact of the outliers. But when we're thinking about using data and analytics in the real world, it turns out that the outliers are what we really want. The outliers are the ones that really are indicating that we've got behavior that does not fit with the normal model, and it might be something that we actually need to act on. So outliers aren't our enemy. Outliers, turns out, they can be our friends. Outliers show us unusual behavior, and they're data points that don't fit with the others. That fits our normal understanding of outliers. But now if we actually apply them to the real world, we can see that they could be indications of things like unusual purchasing patterns, customer behavior that seems out of character, and matching data points against a history of normal behavior. They could be opportunities for us to identify when the customer, who has got a history of maybe 6, 7, 8 years of purchasing kind of the same amount in the same periods, using his or her debit card for the same kinds of purchases, suddenly there's some kind of an outlier out there that just does not fit the pattern. That's what the banks are doing today. They're finding those, and I'm sure that if you haven't gotten a call, someday you're going to get a call from your bank, and they're going to say, we saw this purchase on your account, and we think it's unusual, and we want you to verify that you actually made it. That's great, because if you didn't make it, then they can catch that really fast. But again, those are outliers. Those are outliers from your normal purchasing pattern, and that's what the banks are using to be able to sort of, save you from getting all your money stolen. Other examples are credit purchases. Well, that's the one I just used. Credit purchases that don't match your previous behavior. Use of phone or other utilities. You might get a call from your phone company if somebody all of a sudden hacks your phone and they're taking off and placing all these international phone calls on your phone. What's going on? The phone company can flag that because that becomes an outlier relative to your normal behavior. And also medical measures. Medical measures become outliers based on, again, your past behavior. So it can either be your past behavior or it could be just general behavior that the companies are tracking, where they're seeing sort of a spike in something or some sort of event happening that is leading them to say, wait a minute, this is an outlier and I really need to take action on this. So in the real world, it may be outliers that we care about the most. So again, focusing on the outliers. If we're looking at, for example, our Christmas sales, remember this is our projection of Christmas sales based on sales for the first 11 months of the year, and we start seeing something like this. What's going on here? What happened here? This is a customer who spent, in the first 11 months of the year over $1,400 with us, and suddenly at Christmas time, when we would project that he would probably spend quite a bit with us, he didn't spend anything with us. Is that an outlier that is actionable? Is this customer suddenly very disenchanted with our company? Or what happened? What happened in that particular case? This is to the lesser degree something similar, but it's close to $1,000 in sales, and then all of a sudden in the last month of the year there's only $50 in sales. Well, what happened there? So we have these examples of these outliers. Now normally if we were looking for a nice clean distribution across the mean line, we might be tempted to throw these out. But now we're not going to throw them out, because now we're going to take a look at them and say, well, what happened? Somebody needs to call this customer and say, you spent $1,400 with us, but you didn't spend anything at Christmas time. What's going on? Well, probably in more salesy terms than that. But each one of these could represent an example of some actionable item. This one down here, well, the customer's spending a whole lot at Christmas time and didn't spend very much during the year. So maybe that one's worth looking into. Now this is a data set of about 40 data points, and you might be dealing with a data set of about 40,000 data points, and you want to look at your most extreme examples. But that's where the outliers actually come into play and where the outliers start to mean something. So how do you find your outliers? Well, there's a couple things you can do. Remember the plots that we've done in R, you can do a simple visualization of data points. That's what we just did. That plot was pulled from R. So you can look at them and see what are they. Ideally, those data points would have identifiers on them so you could actually track them. You can look at means and standard deviation analysis. Remember that if you have a large difference between your mean and your median, you probably have uh, outliers that are at play here. And also, if you have a high standard deviation relative to your mean, you probably have outliers that are at play. You may have multiple outliers that are at play. But looking at your mean and median, you can see the direction. If there's a big difference between mean and median, the direction where the mean is either on the left or the right will tell you where your outliers are. You can also look at linear regression models. Is the error between the model and the real measure high? In other words, we've got that linear regression line. Let's go back actually. This linear regression line shows us where our data points are most likely to be. But if we start seeing a bunch of data points where they're kind of all over the place and not really falling on that line so well, in this case we don't have that many because we just don't have that many data points, then there could be outliers in this data set, and there'd be ones we'd want to actually check on. Clustering. Earlier in the quarter, we talked about k-means clustering. If we were to run a k-means cluster on a data set and we were to use, say, 5 means, if we find a group where there's only 2 or 3 or 4 data points, whereas the other groups actually have a whole lot of data points in them, we may find some outliers that way. So it's up to you whether you decide to remove your outliers and rerun your tests. You just have to determine the significance of your outliers. Again, if you're looking just at the mathematical fit, you may want to remove the outliers if they don't contribute anything to the analysis. But if you're looking at sort of application of real-world use of some of these tools, the outliers may actually be where the richest information is. So, lastly, outliers might be exactly what we're looking for. Might even be the focus. Those things that conform to expectation are of little interest. And that would be in the example of where we're actually trying to track credit history or credit patterns. Those people who conform to their typical credit patterns, not really that interesting. But those people who we see a sudden spike in spending, or they're spending in different ways, or they're spending in different countries, that's going to draw some attention. And so that would be an outlier that we would want to track. And again, it will all depend on the data being analyzed and the problem under consideration. So that is outliers. This week that's the chapter we're looking at. I'll have you read the beginning of the Foreman chapter. There's a lot of stuff that follows, just like all of his other chapters, where we can get into the actual mechanics of how he does it in Excel. I'm not going to have you worry about that. Just go ahead and run through this presentation and read the beginning of that chapter, and I will also post a presentation for the work that we're going to be doing in R this week.